Hi, everybody. So in this lecture, I'd like to talk to you about internal energy and heat and define those quantities. So first, I'd like to give you a little bit of historical background into thermodynamics. It used to be that thermodynamics and mechanics were considered to be different branches of physics, and this was the case until about 1850, when James Joule and some others showed that there was a connection between what was thought to be different branches of physics. We'll talk about Joule's experiment in just a minute. And that famous experiment showed the connection between the transfer of energy by heat in a thermal process and the transfer of energy by work in a mechanical process. And so doing united these, what were thought to be separate fields. At that time, then, they generalized the concept of energy to include internal energy, and the law of conservation of energy emerged as a universal law of nature. So what is internal energy? Well, internal energy, or sometimes thermal energy, we call it, is the energy of a system that's associated with all its microscopic components. And this means the motion of its atoms and its molecules. We call it internal because you can't see it with your naked eye. You can't really see atoms of an ideal gas singing around the room, for example. And if you looked at a pocket of air that's, 20 degrees Celsius looks exactly the same as air that's 40 degrees Celsius. You can't really tell by looking. It's something that you have to feel or measure. So it's internal energy. Now, the kinetic energy due to the net motion of an object through space isn't included in the internal energy. So let's say that you measure the temperature of an iron bar, right? That's the internal energy. That's associated with the internal energy. But if you throw that iron bar through space, that's external energy. You can see that happening. So that's not what we mean. The internal energy does include the kinetic energies due to the motion of the molecules and atoms that make up the substance. So this could be random translational motion, like in an ideal gas, or if you have a solid or a liquid, it could be the rotational motion or the vibrational motion, the rotational motion of the molecules and the vibrational motion of the atoms within the molecules. Internal energy could also include the potential energy between molecules as well. Now, people get heat and internal energy mixed up sometimes. So let's be careful to define our terms. Heat is the transfer of energy across the boundary of a system due to a temperature difference between the system and the surroundings. So I like to think of putting a pot of water on a stove when I think of heat. I have a hot stove burner, and then the water in the pot gets heated up because they're in thermal contact, right? So that's heat, transferring the energy from the stove burner to the water. We're also going to use the term heat sometimes to represent the amount of energy that's transferred by that method. So it's easy to imagine putting something in a fire or putting something on a hot stove and transferring internal energy to the object that way. But what James Joule did was he showed that the internal energy of a system could also be changed by doing work on a system, mechanical work. So both heat and work can change the internal energy of the system. So the internal energy can be changed even when no energy is transferred by heat and just by work, like compressing a gas with a piston. In that case, you're pushing on the piston and that heats the gas up, for example, if you compress it. But hey, there's a really simple demo that you can do yourself at your desk. If you just take your hands, put them together and pretend that it's a cold winter day and rub your hands together real fast, right? You can feel that your hands heat up in response to the rubbing of one hand on the other hand. And that's also transferring energy to your hands by work. Specifically, in that case, the friction in between your hands as you rub them together dissipates the energy from the mechanical work and turns it into an increased internal energy in your skin of your hands. So that's a really simple demo that you can do. Now, the first law of thermodynamics that we're going to talk a lot more about later is a special case of the law of conservation of energy. It just says that if you have the internal energy, which I'll symbolize by the capital letter U here to go with the convention of this textbook, that if there's any change in the internal energy of the system, that has to come from either heat or work or both. So mathematically, we state that as delta U, the change in the internal energy, is equal to the heat, which we often symbolize by Q, plus the work, which you're probably used to seeing symbolized by a W. So energy is conserved, in other words. If internal energy changes, it comes from heat or work or both. And so what that means is that the units of internal energy, the units of heat, and the units of work must all be the same. And so the SI unit of that is the joule, named after this gentleman right here, James Prescott Joule. He was a British physicist who lived in the 1800s, and he did a lot of work that led to the development of the first law of thermodynamics. And so in his honor of that work, we named the unit of energy after him. Now, what was his most famous experiment? Well, here it is right here. So this is a little schematic of the experiment. What he did was he showed that you could transform mechanical energy into internal energy. In other words, that you could use work to increase the internal energy of a system. So the system that he was increasing the internal energy of here is this container which had water inside of it. And then you can see that there's these paddle wheels inside the water, and he had a thermometer in there to measure the temperature of the water. Okay, so what he did was he had these weights that he hooked up via ropes over pulleys to a crank here, and he cranked the weights up to a given height H, right? And then he let go of the crank and he let the weights fall. And then as the weights fell, they caused the crank to turn, which turned the paddle wheels. And then when the paddle wheels turned, that agitated the water, and it converted the energy of the falling weights into an increased temperature of the water, which he was able to measure. Okay, so that showed that there was a direct conversion in between the mechanical energy of the weights from the gravitational potential energy and when they started into kinetic energy as they fell and reached the bottom, right, into the internal energy increase of the water. He showed that those were directly related. And what he found was that it took about 4.18 joules of mechanical energy to raise the temperature of the water by 1 degree Celsius. And later, more precise measurements determined that the amount of mechanical energy needed to raise the temperature of the water from 14.5 degrees Celsius to 15.5 degrees Celsius, there was a little bit of temperature dependence there, depending on what the initial temperature of the water was. So we now call this amount of energy that it takes to raise the temperature of water 1 degree Celsius, we call it the calorie, okay? And 1 calorie is 4.186 joules. So this is known as the mechanical equivalent of heat, okay? Historically, the calorie was the unit used for heat in old school thermodynamics, right? And this came from the idea that when people first started studying thermodynamics, they thought that heat energy was this special thing, and that when heat energy was transferred, that there was a kind of fluid called the caloric that was transferred from one object to another. And now we understand that there is no caloric, that that's not a real thing, that the increase in heat is just the motion of the microscopic components of the object. But at the time, you know, it was that was the way that they wrapped their head around it. And so we still stick with the calorie. And of course, the calorie in SI would be 4.186 joules. And you might have heard of the calorie before, but you probably heard of it in terms of food. So one thing that students find a little confusing is that the calories that are written on food packages is actually not this calorie. It's not 4.186 joules, but it's in fact a kilocalorie. So you might have seen that abbreviation on some food packages, especially if you've been to Europe. They'll say that instead of, you know, like 10 calories, it'll say 10 kilocalories or 10 kcals. Okay, so a food calorie is actually 1,000 regular calories. Now, another unit that sometimes gets used, especially in buildings and things like that, is the British thermal unit, or BTU. And 1 BTU is the amount of energy transfer necessary to raise the temperature of 1 pound of water from 63 degrees Fahrenheit to 64 degrees Fahrenheit. So that's another very non-SI unit for heat energy. But please understand that all of these are energy units. A calorie is a unit of energy, a joule is a unit of energy, and a BTU is a unit of energy. And the SI unit of energy is the joule, okay? And that's what we're going to use in this course, except in example problems where I'm specifically requesting that you change energies units from calories to joules or something like that. People also get a little confused when they talk about temperature because they think of temperature sort of like they think of energy, but these are actually different things, okay? Remember that temperature is associated with how hot or cold something feels, and temperature is how we measure internal energy. In other words, I'll show you an equation in just a second, which shows a direct proportionality in between temperature and energy. But please understand that these are different things. The SI units of temperature are Kelvin, and then also English units or other units that get sometimes used are Celsius or Fahrenheit. But this is not a unit of energy, okay? It's a unit of temperature. And then you have to then do a calculation to get the internal energy from the temperature. So the internal energy, as I said, is proportional to the temperature. The equation that relates the potential or the internal energy and the temperature depends on what kind of substance that you have. So we've already talked in previous lectures a lot about ideal gases. So I'm going to show you the equation for the internal energy for ideal gases since we've already talked so much about them. In a previous lecture, we showed that for a single molecule of an ideal gas, that its kinetic energy as it zings around the room, bouncing off objects, is proportional to 1/2 mv squared, where you're taking the average value of v squared for the molecule. And I'm saying that it's the speed squared average, right? Because, of course, if you average over the whole gas, you might have different speeds. And so this is an average ideal gas molecule at a temperature T will have this average speed squared. I hope that makes sense. And the bar over the top of the V squared symbolizes the average. So the average kinetic energy for a single ideal gas molecule is 1/2 mv squared bar. And then we showed in a previous lecture that that was proportional to the temperature of the ideal gas by 3/2 kT, where K is Boltzmann's constant, okay? Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin in SI units, and T is the temperature in Kelvin. So you can see here that the average kinetic energy of a single molecule is proportional to the temperature that the gas is at. And what that means is that, you know, this is for a single molecule. If you have a collection of big N molecules, right, large N numbers of molecules, then what you would do is to get the total kinetic energy, you would multiply the average kinetic energy for a single molecule by N, okay? So the average total kinetic energy would be 1/2 N mv squared bar, right? And that would give you the total kinetic energy for the collection N. Now, since you're just multiplying the left-hand side here by N, you multiply the right-hand side by N too. And that gives you 3/2 NKT for the average kinetic energy of that collection of molecules. Now, think about this. The internal energy is the energy that's due to the motion of the atoms or molecules of the gas. Now, for an ideal gas, you just kind of have this one molecule, right? And it's just zinging around the room. So its translational kinetic energy, average translational kinetic energy, is its internal energy. That's all there is to it. And so we can, for ideal gas molecules, set the total internal energy of the ideal gas equal to 3/2 NKT. Now, if you know the number of moles, little n, instead of the number of molecules, big N, then you can also write that as 3/2 nRT, little n RT, where little n is the number of moles, R is the gas constant, and T is the temperature. The gas constant R in SI units is 8.3 in SI units. Okay, so let's do an example problem, a quick example problem, talking about these ideas. So let's say that you're trying to lose some weight by hiking up a hill. So how high up the hill do you have to hike in order to burn off 1 food calorie? Okay. So 1 food calorie is 1 kilocalorie or 1,000 regular calories. So that's 4,186 joules there. Okay. So how high do you have to go to burn 4,186 joules? Well, you're conserving energy here. James Joule showed us that, you know, if you have some weight and you're moving it through a change in height, that you can set that equal to the internal energy change of the system, right? Okay, so that means that we could set MGH, which is the change of potential energy that you would undergo if you hiked up some height H, right, M is your mass, and G is the gravitational constant, 9.8 meters per second squared. So you set that equal to 4,186 joules. Now let's say that your mass is 70 kilograms, and of course G is 9.8, and then you're solving for H. So you divide 4186 by 70 times 9.8, and you get H is equal to 6.1 meters. If you convert meters into feet, that's about 20 feet. Now, that seems kind of like a lot to climb just to burn off 1 calorie, right? 1 food calorie. But the good news is that your body is only about 20% efficient at that. So you'd really only have to climb about 4 feet. If you take 20% of 20 feet, you'd only have to climb about 4 feet. But that's per calorie. So if you're trying to burn off a dessert or something, that's a lot of feet, okay? So be careful. All right, well, I hope you understood that. I hope it made sense, and I will see you in the next lecture.